Hello. So this is a joint work with the French Space Lab ONERA, the CNES, the French Space Agency, and Airbus Defence and Space. So today we are talking about an Earth observing mission, and it's part of a technological program from the French Space Agency, which is aiming at developing the next generation of agile Earth observing satellites. So we are interested in planning of satellite activities, and we are focusing on data download planning. So I will explain now the system, how it works. On this scheme, you can see there are some users. So it can be companies, scientists, or states. They are asking for observations, and they are sending it to the mission center. Every 8 hours, the mission center is building a plan. So an observation plan, a data download plan, and other activity plans, and sending it to the satellite through a control station. Then the observation satellites do the observation and then download the observation through ground reception stations during visibility windows. So windows during which communication is possible between the satellite and the ground reception station. I do not mention this or this. Then the ground reception station send it to the production center, which produce the real images that will be delivered to the client, and then it's delivered to the user. We also have like some communication about health status or general state of the satellite. So today we are talking about the data download problem. So it's an oversubscribed problem. It means that there are too much things to download for the capacity of the downlink. The data of the problem is the observation schedule and attitude profile. So yeah, agile Earth observing satellites have an attitude profile. They can move. They have 3 axes of freedom, so they can move in a lot of ways, and that makes planning a lot more difficult. And we also have ground station visibility windows. So I talked about that. And onboard, how does it work? So you have the instrument here. So the instrument is made of detector lines, 1 line per frequency. And when you are taking a picture, when you are doing an observation, you are putting on some of the lines. And then it produces a file that is going through data compressor. And that's the main point of uncertainty in that application. The data compression is not known in advance. It depends on what is acquired. So we'll see that. Then a file is produced and put into a memory bank. Then when you want to download something, you have to take the file from the memory bank and then put it on channel. And then you have several channels, concurrent channels that can be used for downloading. So this is a very simple example of what a data download plan looks like. So we can see the different constraints. So here you have the visibility windows. So during which communication is possible with ground. You can see that it's overlapping. So sometimes the satellite sees several ground stations at a time, but it can only communicate with 1 station at a time. And what you see here, it's this rectangle. It's what we call the download window. So it's the time during which communication is effectively happening. So this is the download window 1 on station 1 and the second. And here it's a file download. So an acquisition, an observation, an image is made of several files. And so here in this example we have A, B, C, D, E. So we have 5 observations, and we have 7 files per observation, I think. Yeah. So we can see the different constraints. So for example, the precedence canal use. On a channel, you cannot download 2 files at a time. Okay, that's the red constraint here. Also, a memory bank, files are stored on memory banks. You cannot read several files from the same memory bank at the same time. So that's the blue precedence. So it means that on the same memory bank, you have a complete order. Also, you cannot download something before it's finished. So when the acquisition is not finished, you have to wait to download the acquisition. And at the same time, we have a deadline. So we have to download acquisition before it's not useful anymore. Also, we have some time-dependent constraints. So because the satellite is agile, its position is changing during the time. And so the time it takes to point a station or another station, it's changing also because of the position of the satellite. So this constraint here, to go from a station to another, it's a time-dependent scheduling. So it depends, the duration depends on the time it starts. So that's a very simple example. This problem, so it is the reunion of several subproblems. When you allocate observation to visibility windows, you can think of a multiple knapsack problem, which is strongly NPR. And when observation are on visibility windows, you have to schedule the files. And so you can think of a flexible open shop or a parallel machine scheduling. And when everything is done, when you have solved the first 2 problems, you just have to compute earliest start dates for every download. And that is polynomial, since it's a time-dependent simple temporal network. So, and so it's an optimization problem. So we have a criterion. So what is the criterion? We have a need to favor a high priority download. So we have high priority observation and low priority observation. So we want to favor high priority. We also have the notion of fair sharing. Like the users, they put money into the system, and we want that the system be allocated to the users according to their investment. So we have a notion of fair sharing, and also we want to maximize data freshness. That is minimizing the time between the observation and the download. So we have a hierarchical criterion. I will not detail it, but just remember that it aggregates a lot of things into one criterion. And we can dosage between utilitarianism and egalitarianism when we are talking about fair sharing. So the uncertainties. So the cloud cover. We cannot say exactly beforehand if a cloud will be on top of the objective, because when we are observing something, we have an objective. We want to observe maybe a city. Maybe there will be a cloud. And because the compression algorithm is working with the clouds, we will see, it will affect the file volumes. For example, the compression algorithm will not do anything with this picture. It's the city of Toulouse in France. And it will not do anything because it's very dense. It's very dense, and there's a lot of information, and we want to keep all the information. But here we have a lot of clouds. It will compress all the clouds parts of the image. And here we have another image which is low density, so it will compress a lot also. So yeah, file volumes are known only on board, not on the ground. Also, we have other uncertainties. So how can we deal with these uncertainties? How can we plan things if we don't know the volume, if we don't know the durations of the tasks? So we can have a deterministic offline planning approach. It has been done. when you want the plan to be always executable, you just take a lot of margins on everything, on every uncertainty. You take the maximum volume, the minimum energy. So this has been done, but it's not very efficient. You have the robust offline planning on the ground. So it's an approach. You have the offline synthesis of policies, such as MDP, for example, but it's not applicable regarding the problem size. We're talking about like 5,000 plus tasks. We have the onboard scheduling approach. Like, because all the uncertainty is on board, why not just take all the decision on board? It has been tried, but the problem is we have limited computing time on board, and also on board we cannot take the criterion because it's very complicated to compute. So we want to do another option, flexible scheduling. It means a part offline on the ground and a part online on board. We want to separate things. So we want to build flexible schedules on the ground that are partially instantiated and easy to adapt. So it relates to partial order, list commitment, or robust scheduling or planning. The problem is computing time and power are very limited on board, so we cannot do any complete search or, I don't know, local search, or we need to have a very tractable algorithm on board. And we also have a special need, the need for the system to have a predictable behavior. It means that we need to ensure that some of the observation will be downloaded, and we need to ensure where it will be downloaded. So that's a special need. So how do we do that? We have a 24-hour planning horizon on the ground, and the plan is recomputed every 8 hours, so on a moving horizon. And what we say, we have two priorities. We have high priority observation and low priority observation. We say that we want to ensure that all high priority are downloaded. So all high priority observation have a commitment. So that means that we are sure they will be downloaded, so we have to take the maximum volume for these observations to ensure that the plan will be executable. But for the others, we will take the mean or expected volumes. Why? Because first, we are not really hard on downloading this observation. We can download it later, and also you can look to that article that says very roughly that in a large STN, simple temporal network, you can disregard duration uncertainty because it will be cancelled when executing. So the objective is, so we talk about commitment. So we want to be sure that an observation will be downloaded so how do we do that? We take maximum volumes, like I said, and we schedule on channels the memory bank to be sure that it will be found. And then we transform a complete plan like you have seen into a flexible plan. So we just remove all the unnecessary information, and we will recompute a plan on board. But with this plan done on the ground, we will have much less computation to do on board. So we do a squeaky wheel optimization scheme on the ground to find a plan, but it's not very relevant to the presentation. I will show you just how it's done, how the algorithm on board is doing. So on the ground, you have, let's say you have 8 observations, 4 high priority observation and 5 low priority, 4 low priority observations. So that's the plan we have on the ground. And we have a complementary list. It means that this observation were not scheduled on the ground. So to help the onboard software, we will produce some latest start dates for the high priority observation, so that we can know very quickly if a low priority download will impeach a high priority download to execute. Like for example here, how do we do that? We have the baseline plan. We just remove the low priority observations, and then we push the high priority to the end, from the end, and we deduce these latest start dates. We will see how they are used later. So on board, you have only two changes. One is one high priority observation is lower, has a lower duration than maximum, and one low priority has a higher duration than predicted. So how does it work? Basically, the algorithm on board is just following this plan, and when it can add something because it's possible, it does it, but always by looking if it will not prevent any high priority observation from removing. So it really follows the plan. And here, for example, we have time before the beginning of A2, so we insert a new acquisition from the complementary list. I will skip because it's very simple, it's greedy, it's chronological. And we have done some experiments on realistic instances provided by our industrial partner. And you can see here that the instances are pretty huge. So it's it's difficult. We are comparing 4 approaches. Ground, it's just observation scheduling with maximum volumes for all, and the plan is strictly executed on board. Simple repair, I do not talk about this. Smart repair is the procedure we have seen. It just follows the flexible plan and inserting acquisition that can be inserted, and board, that is an onboard procedure that is chronological and that does not take into account any flexible plan produced on the ground. It's just on board. So what we can see here, it's the number of downloaded observation. We take a look at the low priority observation, and we can see some differences. So basically, the board approach, the onboard approach, is the best here with the smart repair approach. So the repairing approach is doing almost as good as the board approach. Here, the mean information age, that is very important. So here on the ground approach, we can see that it's the worst, of course, because all the maximum volumes are taken. So there are not a lot of acquisition that are downloaded. Again, the onboard approaches are the best. And here we have something interesting. So the complete criterion, the very that aggregates a lot of things. We can see here that the best approach is smart repair. It's because smart repair is a mix between ground and onboard. So the ground can take into account this kind of aggregated criterion, while the pure onboard approach cannot. Here, a very important thing for space operation, onboard computing time. We can see here that the board approach is taking a lot of time, while the smart repair is using flexible plans, so it does not have to compute a lot of things. In conclusion, we have to deal with an assignment and scheduling problem, and it's kind of a new decision-making architecture for space operation where operations are shared. And we would like to improve the robustness measures and testing on a real satellite case. Thank you.